everyone. So, this is going to be module 13B. When this one, we're going to focus on successive approximation ADC, but primarily using the ADC0805. I think that's the one we're using. Let me double check quick. Yeah. Yeah. ADC0805, which is the successive approximation ADC we're going to be using in lab. So just describe how that works. But just a reminder, right? The ADC that we use in most consumer electronics are these successive approximation ones, which are slow, but they're cheap. So that's why they're used in everyday, so that your cell phone doesn't cost, $100,000 to build. Okay. Now remember that the successive approximation algorithm, ADC, works on this algorithm called binary search, where basically you're successively kind of going through this over and over and over and over and over again, guessing, right, what the value is, and then every guess gets you 50% closer to the actual answer. And then you have this Zeno's paradox of getting halfway closer to the answer every time you go around this cycle. And this cycle takes multiple clocks takes in order for it to happen, because, right, you have to do the comparison, and then you have to do the logic, and then you have to register the values so you can record it, and then you have to forward it to the DAC, and then that DAC value comes back to your comparator again. Okay, so this takes multiple steps. And we talk about how, this is basically like a binary search, so I'll let you go through the lecture videos again if you don't remember it. But if you're guessing the number is 9, then you just do multiple guesses in order to get to as close to the answer as possible. Okay. And the main thing is that it took 4 guesses to do a 4-bit, and then if you do an 8-bit, it will take 8 guesses, and if you're taking 16-bit, you'll take 16 guesses, right? So notice that when we're guessing that it's too large, what you're doing is you're shifting the bits from to the right, which is just a shift register that we learned about from a previous module. Okay, but if the comparator tells you that, oh, your guess is too small, right, we keep the current bit and then shift it to the next bit instead. Okay, this is actually a flip-flop latch logic plus a shift register. So we'll look at how that so you can see that how this logic inside this SAR part, right, it actually works. Okay. But the main thing is that each of these steps takes at least 1 clock cycle to do, right? So you do a guess, you do a compare, and then you send, and then you change the next guess, right? And then there's usually a +1 for you for this to do the comparator. Okay. Sorry, there's an extra cycle used as a buffer or error checking. So each time you guess, it actually takes about 4 clock cycles just to get through it, right? So the example I gave, like if you're doing 4 bits, right, 4 times 5, it takes 20 cycles in order to do it for you to do 1 analog to digital conversion. Okay. In the lab, you're going to be doing 8-bit analog to digital conversion. Okay. And using an internal SAR, that should take about 40 cycles. Okay, that's just internal to the SAR, the successive approximation register. In reality, there's a little bit longer because you're going to have to do a sample and hold, and we'll talk about how that sample and hold work. And then you're also doing a comparator, so you have to be a little careful about delaying things so that your comparator has time to switch from high to low in case that changes, right? So you usually have to add another 10 cycles on top of that. There's also a little bit of, in order to interface with something that's a computer, there's also this end of conversion key that you have to allow things to settle down and put the digital data or clear the device before your next input. So there's a lot of handshaking and that also takes another 10 cycles. So not only do you have to do all the SARs, the conversion part, there's a lot of little overhead you have to deal with. Okay, so usually the number of cycle it takes to just do an 8-bit conversion is about 60-ish. Okay, so in the lab, you're going to get to work with the ADC0805, which is the chip that we have. It costs about $10. It's actually probably the most expensive chip in our class. Yeah, it's the most expensive chip in the class. Um, and but you know, if you were doing this, the flash version of this would cost, you know, $500 to $1,000 instead, right? So it's still much cheaper. Okay. So it does one conversion into 8-bit every 66 cycles. So, you know, what I estimated before is approximately right. So you need at least 40 to do your little conversion, and there's some overhead to hand off the data and then hand out and then erase the data so that you have it ready for the next run. Okay. It's kind of a complicated integrated circuit. So this is data sheet. The one we're going to be using is going to be this latest version. The ADC means ADC, so 8 means 8 bits, right? And then 5 is just like the latest version. Well, maybe it's not the latest anymore since these are pretty old. Okay, I'll let you read through that. We'll try to do some exercise in the pre-lab to make sure everybody understands how to use this thing. Okay, but the main thing is that it's 8-bit conversion. The input can range from 0 to 5 volts. That's the only input you can get. Okay, so let's say if you have a 0 to 15 volt input, what you need to do is put that through a voltage divider in order to limit it from 0 to 5 volts. Okay, so 8 bits gets you 256 levels. Okay, so you can see that the number of conversion time takes 66 clock cycles. Okay, in fact, if you try to go at the maximum speed, it's actually slower. Interesting. But it's a big chip, so it has 20 inputs. Well, 20 inputs and outputs. Let's see what's important to know here. The clock in here, I'm just going to highlight instead. So the clock in here, right? That's the clock frequencies on these conversions that you see up here all the way to the top, right? This is the clock in that we're dealing with. Okay, so the faster that clock, right, even though it takes 66 cycles, right, if the period of this clock is shorter, right, you can do 66 things quicker if the period is shorter. So we're going to start you off pretty slow, but then we're going to drive things a little faster and faster. And then and if the thing is, if you run at full speed, this chip actually heats up. So usually they even have a little heat sink on top of it, but we're not going to have that, so because we're not going to run at full speed. These are the inputs, right? B in, B minus. One neat thing is that it does a second reference so that so it runs from 0 to 5 volts, right? But it also wants a voltage divider that gives you exactly 2.5. So you want to pick those two resistors very carefully so they match it with each other. You have your voltage sources. This is your analog ground. This is your digital ground because those could be different. Okay. This is the ready, right, and this is the conversion set key, but these are always flip logics. So if you want things to be ready, right, the ready bar, you actually have to be 0. So when something is ready, you actually want to send 0 there, and that way you flip that logic to 1, so now it's ready. Okay, to ready to convert or write, to read or write to your ADC. So that's what these are the extra clock cycle that gets built into it. That's why it gets blown up to 66 clock cycle. This clock R, this is the resistor part. So instead of an external clock, you can actually have it connect to an internal clock. So we can you can actually just run this chip without a function generator, for example. But then the stuff on the right, is the 8 bits, hopefully, right? 11 to 18 gives you 8. Those are the 8 output binary output bits. Okay, and then the lowest one is the MSB, which means is equal to 2 to the is equal to 128. So and then the 18th bit, the pin 18 is actually the LSB, which is the the one that gives you ones and zeros. Okay. Oh, CS is chip select. Okay. Um, okay. Oh well, a lot of the descriptions are down here, so I'm gonna have you look this up anyway. The conversion time is approximately 100 microseconds if you run at a frequency of 640 kilohertz, which is actually, I think, the maximum speed that it can run. So, conversion time of 100 microseconds, that means 1 millisecond can do 10, so it can do about 10,000 conversions per second, which is good enough if you're doing like sound, um, um, or anything even slower than that. Okay, but that's probably the best it can do. Okay. You can also, yeah, so I was going to mention that, so instead of using the external clock, you can also go into use this clock R thing, where if you connect clock R and clock in together with a capacitor between them, and then a resistor between them and a capacitor between them, that's 150 picofarad, right? If you calculate this, the frequencies you're going to get is 1 over 2 pi times 10k times 150 pico. That's going to give you 100 kilohertz. So if you want to reduce this internal clock, you can reduce this this resistor, but you don't want to reduce this too much more, because it cannot go faster than 640 kilohertz. So maybe you want to have this meaning if you want this frequency to go up by a factor of 6, you reduce this by a factor of 6, and you'll get there. But that's running it at the maximum speed, which actually heats the chip up. So we're not gonna do that on the lab. Okay. But the thing to remember is that just because the clock frequency is 100 kilohertz, you don't get 100,000 conversions per second, because it takes about 70 clock cycle for it to do one conversion. So because this is a successive approximation ADC, not a flash ADC, right? The thing you want to also note is when we're using this, we're going to use a sample and hold with it. This is the LF398. And the idea of sample and hold is that you can have an analog input here, and then you have a logic input here. So whenever the logic goes high, it samples what this is, and it holds that value for a microsecond. That way you can do your analog to digital conversion without having the value change too much as you're doing that conversion. Okay. And we're going to have to use that in the lab, because the successive approximation register ADCs are so slow. Okay. And I'll let you guys work through the homework to pick which capacitor to use, so that the droop is right and also the acquisition time is good. Okay. But that's just picking the right resistor to set up here, this holding capacitor. I keep mixing resistors and capacitor up, sorry about that. But this is a holding capacitor. Okay, so I think this lecture is pretty short, because a lot of this you're going to see in the lab. I just want to go through it. That way you know why am I forcing you to work on a sample and hold first, because that's just preparing the whole thing, the circuit, so that you actually can do the ADC at the end. Okay, so that's all for this lecture, and then next one I will wrap up with doing this on FPGA. Okay.